Greetings. In this video, I'm going to talk about inference about two means. There should be an S there. When we have independent samples. So I just want to be clear that there are situations where you have dependent samples. That's often called a matched pairs design, and that's something a little bit different here. So these strategies pertain to independent samples. All right. So two big ideas for this video are going to be a hypothesis test. And then we'll also discuss confidence intervals. So the idea here is that we have two different populations. I'll call this population A and population B, and there is a mean in population A and a mean in population B, and we're wondering how those two compare. So maybe if this would happen to be larger than this one, or the opposite were true, where this mean is larger than this one, or if they just differ in some way. So our strategy is that we're going to take a sample, and we're going to look at the sample mean from group A and the sample mean from group B, and says examine the difference between these two. So let's get started. First I want to talk about a hypothesis test for the difference in two means when you have independent samples. The null hypothesis here would be that the mean from group 1 is the same as the mean for group 2. And again, a hypothesis test is about this parameter, so the population value from mu. The alternative hypothesis could take on one of three forms. Either the first one is less than the second. You could have the first one is greater than the second, or alternatively, you might say that the mean in the first differs from the mean in the second. So the statement in the alternative hypothesis is important. It determines the type of test we're doing, whether it's going to be a left-tailed test, and that would be in this situation, a right-tailed test, that would be true here, or a two-tailed test, which would be in this last scenario. So it turns out that when we look at this X bar from group 1 and X bar from group 2, if we take the difference in those, this statistic is approximately follows a t-distribution. And so we can conduct a t-test. So the idea here, and this is true of any t-test, we've got this t-distribution that looks like, I always just draw a standard bell, and if we have, for instance, a left-tailed test, then we're going to have some sort of a cutoff point in the left tail, and there will be a critical value associated with this line, and that's the placement of this line and the critical value depends on your alpha, your level of significance. So if I get a result that's in this tail, we call it the rejection region. I'll reject the null hypothesis. But if I get a result over here, I will fail to reject the null hypothesis. So that's if you're using the critical value method. Well, we would need to compare a test value to our critical value. But remember, we also have the p-value method, and where you can compare a p-value just directly to your level of significance. So in order to conduct this test, we're going to need a little bit of information from each of our samples. So namely, from group 1, not only do we need the sample mean, we also want to have the standard deviation from that sample and know that sample size. And I'm actually going to switch to using subscripts of 1 here. And from the second population, I'll take a sample and I'll look at that sample mean and that sample standard deviation and the sample size. The test statistic then, so this is going to be a t-test, looks like this. We can take this x bar 1 minus x bar 2, and then in the denominator we have this big square root with s1 squared over n1 plus s2 squared over n2. Now technically there is another term here, mu1 minus mu2. Now, since the null hypothesis is usually that those two things are the same, then this difference is in all the examples I'm going to be doing, this difference is just 0, and so we can just leave that off. Now, anytime we have a t-test, we need to know degrees of freedom. So there is a formula for calculating the degrees of freedom, and it's rather complicated. Most people just say the lesser of n1 minus 1 and n2 minus 1. So whichever sample size is smaller, just subtract 1. Now if they both happen to be the same, then you just take the sample size and then subtract 1. So we'll be using that degrees of freedom. That's going to be necessary in finding this critical value. Remember, for the inverse t function, you'll need to know the area and then degrees of freedom in order to find t critical. All right, so let's look at how we can use our calculator to give us a little shortcut here. Let's say that we have summary information from 2 different populations. We'll call this sample 1, and this is going to be sample 2. And we have n equals 15. That was the sample size for the first group, and maybe it's the same over here. Here we get a sample mean of, say, 15.3. And here we get a sample mean of 14.2. This one has a standard deviation of 3.2, and here we have a standard deviation of 3.5. And we want to test whether mu1 differs from mu2. So we're going to conduct a two-tailed test. So I'm thinking to myself, first we should probably decide on a level of significance. Let's use alpha equals 5%. So I like to visualize exactly what it is I'm doing here. I've got this bell-shaped t-distribution, and I want to conduct a two-tailed test. So this alpha needs to be split. I'll have 2.5% in the left tail and 2.5% in the right tail. And so first of all, I want to find my critical value. And so since this is symmetric, if I find the critical value from the left tail, I can just take its absolute value, and that'll give me the critical value here. So I'm going to use my TI-84 and look in the distribution menu for the fourth option, this inverse t, and I'll put 0.025 because it's 2.5%. And now for degrees of freedom, both of these sample sizes are 15. Since they're equal, I can just take one less than 15, which would be 14. And I find that this is negative 2.14, and I'm just going to round there 2 decimal places. So now how do I find my t-test value? So under the stat menu, if I scroll over to the test options, there is a 2-sample t-test. It's option number 4. And since I have my data already summarized, I'm going to use the statistics option. And I need to enter the values from my first sample and then my second sample. So x bar 1 is 15.3. Standard deviation from sample 1 is 3.2, and that sample size was 15. In the second, I have 14.2, 3.5, and a sample size of 15. And I'm testing whether those differ, so I can leave that. Select that. And I'm going to use the pooled option in my examples. I'm sorry, no, not the pooled option. So you would use this pooled option if you knew that the populations had the same standard deviation. There's a test for that. It's called an F-test. But if you're not sure, the safer bet is to use this no, and then I can calculate. And so I find a t-test of 0.898, and that has a p-value of 0.377. So my level of significance for the test was 5%, and I have a p-value of about 38%. So I'm definitely not going to be able to reject the null hypothesis. Also, looking where my t-test falls, it's somewhere over here at like 0.898. 0.898. I would need something either larger than 2.14 or less than negative 2.14. But I'm actually getting a value that's actually in the middle of this distribution, closer to 0 than it is to either one of those tails. So whichever strategy you use, whether it's the critical value or the p-value, we are going to fail to reject the null hypothesis. And so that means that there is, if we fail to reject, there's insufficient evidence that mu1 differs from mu2. Now, I do want to just mention there are some conditions that you could check for conducting this test. Make sure that, I'll just write here conditions for test. Firstly, you want to make sure that both samples are random. So you could either have a simple random sample or a randomized experiment. And for this technique, we need to make sure that the samples are independent. So for dependent samples, we would just do something called a match pairs. So that's not the case here. The populations are normal, or we have large samples. Now, if you need to test whether the populations are normal, you could do a normal probability plot and a box plot based on your samples to make sure that you don't have any outliers and that they are approximately normal. But if you have large samples, you can get away with some deviation. So, but in this case, since the sample sizes are small, meaning less than 30, I would want to make sure that these are normally distributed with no outliers. And secondly, we want to make sure that for each sample, that the sample size is less than 5% of our population. So assuming that all these are true, this is a valid procedure for testing the hypothesis about the difference between two means. All right, in another video, I'll show you an example of this with some context, and then even beyond that, I'll come back with and show you how to do confidence intervals for the difference between two means.